are the Quantum Cast, and we're just a bunch of teenagers with a passion for STEM, and we would like to share this passion with you. So I'm Loveleen. I'm doing physics, maths, and further maths, and I just hope to become an astrophysicist.
I'm Amy, and I'm studying maths, further maths, and unfortunately chemistry. And I would like to study maths in uni.
Hi everyone, I'm Chahat, and I'm currently studying biology, chemistry, and English literature, and I'm aspiring to become a dentist. And yeah.
Hi everyone, my name is Aldona, and I'm studying biology, chemistry, and maths, and I hope to study biomedical sciences at university.
That's great. Okay, I say for the first episode to introduce ourselves, we can do a little fun fact each. That would be quite nice. So, my fun fact for the episode is that I can speak 4 languages fluently, and I can speak like French and Spanish, but that's not fluent, so it does not matter. But the fun thing about this is that I'm Italian, as in like my nationality is Italian, and I lived and I was born in Italy, so I can speak Italian, which is related to my topic because I'm talking about Enrico Fermi today, which is an Italian physicist. So yeah, I think speaking languages just makes me a bit cooler, doesn't it? Amy?
So a fun fact about me is, I mean, it's not fun, but I was wanting to study to be a doctor, and I was gonna study medicine, but then, when I took biology, chemistry, and maths at A levels, and I was really jealous of the people taking further maths because they were like talking about imaginary numbers and matrices, and I was like, I want in on that. So I decided to take further maths as well, and I'm really grateful because that made me realize that I actually wanted to study maths in uni. So,
yeah. A fun fact about me is that I initially set out to become a doctor, but then towards the end of year 11 summer and start of like sixth form, I had a major existential crisis because I was like, I don't want to be a doctor. There's too many years to study for, and the pay isn't the greatest, unfortunately, and it just wasn't worth it. So then, after some scraping around, searching around, I stumbled upon dentistry. And that's how I've set out to become a dentist. So that's my fun fact.
My fun fact is that I've been working on a Doom painting for the past 3 years. I've yet to finish it, but right now I've been working on it recently, and I've managed to paint heaven. But I think I painted it in the dark by accident. So you just painted it. No. Like I painted it like the room is quite dark, so I thought
Was it like your room?
Yeah, my room.
Your room was dark and you just painted it dark.
Like there wasn't that much light. It was a pitch black.
Yeah, okay.
So I
okay.
Had it as like a light yellow. Well, I thought it was a light yellow. Yes, you. And then I showed it to my mom, and I put the lights on, and turns out it's like the color of a melon. It's this weird green, and I will be redoing that this weekend.
Great. Do we all want to say what we're taking over, what topic we're taking over for the podcast? So I'm co-handling with Aldona biology and chemistry.
I'm gonna be talking about maths.
I'm gonna do physics and astronomy, which eventually I think is gonna lead a bit into that. But that's about it. That's us. That's our fun facts, and we do hope you stick around for the whole thing. This video will be cut in pieces, as in like underneath you'll be able to choose the section you want to go to. But just listen to the whole thing because we're just great people and we did put a lot of research into it, so you better like and subscribe and comment that like button and do everything
and share with your friends.
Yeah, share with your friends because we're also friends, aren't we?
Yeah, I hope so.
Right, we're also friends, and it's just.
Okay, so I'm going to start off with my topic first, and I'm talking about how oxygen is being made without sunlight. Okay, picture this. Imagine plunging 12,000 feet beneath the Pacific Ocean, right, into total darkness. So there is no sunlight and there's no plants, just an eerie, alienish landscape which is covered in rocks that are like million year old. Yeah. Now, picture those very rocks producing oxygen on their own. And that's basically what I'm talking about today. Okay, so deep in the Clarion-Clipperton Zone, which is also known as the CCZ, it's a rich stretch of land under the sea between Mexico and Hawaii, and it's I think around 1.7 million miles. It's a really big landscape, right? Scientists stumbled upon something that could genuinely rewrite what we know about oxygen and how it produces in life itself. Dark oxygen, which is what we call oxygen that's made under the sea, dark oxygen. So, can rocks make oxygen? Basically. The crazy part is that it's happening without sunlight, and normally oxygen comes from photosynthesis, right? So plants absorb the sunlight, they break apart water molecules and release oxygen. But down there, in the sea's eternal night, something entirely different is going on. Something that we genuinely couldn't think would happen up until now. So the secret lies in polymetallic nodules, okay? And these are basically deep sea rocks which are packed with valuable minerals such as nickel, cobalt, or manganese. Which is also a fun fact, which is I think one of my science teacher's favorite element, manganese, Mr. Hall. Anyways, okay, so scientists call these nodules that they call them basically natural batteries because they generate electrical charges. So, do you have a question?
No.
Oh, okay, just physics. Okay. Now this energy is enough to split water molecules into oxygen, hydrogen. Yeah, into oxygen and hydrogen. Sorry, which is also called it's a process called seawater electrolysis. Yeah. So, in other words, these rocks are basically making oxygen at the bottom of the ocean, which is basically challenging everything that we know about oxygen and how it gets into the world's waters. Now, why does this matter, right? Because, for starters, it raises huge questions, okay? Now, could these rocks be helping deep sea creatures survive in ways we never imagined? What if disrupting the rocks wipes out entire underwater ecosystems? And most importantly, which is one of my favorite questions, could this even challenge how we think about the origins of life on Earth or even life beyond Earth? Yeah, the last one, a big deal. Okay, so I'm going to talk about deep sea mining and how it's a high stakes battle. Now, this discovery came at a time when mining companies were desperate to dig up these nodules, and that's because they contain key materials for batteries, the ones that power electric cars or phones and other technology, right? Now, one company, the metals company, called these nodules a battery in a rock. They argue that mining these could reduce the need for land-based mining, which would basically speed up our use of like renewable energy, which would, it's good for the planet and whatever, right? But not everyone thinks that way because the United Nations International Seabed Authority, which is also known as the ISA, they could basically approve large-scale mining in the CCZ as early as next year. But some countries, including Nauru, Tonga, and Kiribati, support mining efforts. Others like Palau, Fiji, and Tuvalu are calling an outright ban because they're worried that there's consequences that we wouldn't know about, and they would snowball into larger consequences, and basically humans being humans. There's also environmental groups that warn that tearing up these oxygen-producing nodules could irreversibly damage life as we know it underground, under the sea. And with all the deep sea animals that rely on oxygen to survive, what happens if we start stripping apart these very rocks that might be sustaining their survival? Okay, and these are all just like problems that come from all the the deep sea mining. But now, could dark oxygen help us find alien life? Now, the discovery is not shaking up our understanding of Earth, and it's not just shaking up our understanding of Earth. It's making scientists rethink where life could exist in the universe and how it could exist. Yeah.
By aliens, do you mean aliens in the sea?
Aliens, basically, yeah, aliens in the sea. Because I'll get onto this because there's another point, because we could have aliens outwards and space as well, but because we could have aliens under the sea. it links to the point where it's a big connection. Like our sea, because
Right now, we don't even know.
like okay, no, because we've only discovered 5% of the ocean. 95% of the ocean we haven't discovered. So technically, basically, alien could count as anything that we don't know. It's like something it's not quite reachable. We don't have understanding on.
Isn't alien something that's unknown? Like, yes, it is, but it's also like a species on our planet. So an alien would be something else. Like, yeah, but its very definition is something that's more.
Yeah, no, yeah,
we would classify.
that makes sense.
Like, I think it's definitely.
But see, here's where the connection's made. Okay, now, so places that we usually look towards for alien life would be like Jupiter's Europa or Saturn's and Enceladus. Okay, anyways, okay. Now they have vast subsurface oceans.
Yeah.
But they have no sunlight. Right? So basically, if metal rich rocks like the ones we have could exist on those ocean floors, they could be producing oxygen in total darkness, just like in the CCZ. And that basically means that we could have aliens in those oceans that we don't know about, right? Like that's where the link is made. Anyways, so astrobiology, yeah.
Wait, the aliens aliens?
I don't think so. Quite like Attack on Titan. Maybe. See, I'm not very sure, but like, it could just be like any species, like because
Could it be like since they don't have access to sunlight, they've like mutated?
possibly because like we genuinely don't know anything. Like there's so many variations and so many hypotheses around these things.
If we have like a normal fish that we've already like discovered, it lives like towards the top of the ocean, so it gets sunlight.
Yeah.
And if that same fish was living like say at the Mariana,
Yeah, it could mutate differently, like be complete. Yeah. I mean, I guess that's quite subjective. Like, would you classify that as an alien? I classify aliens as something that's like not on our planet. Like some people would classify aliens being like just a species that you don't know that could be classified as an alien to them. Like, yeah, there definitely is like there could be so many variations of like animals or species that we know that there could be so many variations of them, and especially on like different planets, like Jupiter and like stuff.
Yeah, I don't necessarily think it has to be like Attack on Titan. Not that I've seen it, but I don't think it has to be like a multicellular organism. Like
no, it could be like
one cell organism, which is a lot. Yeah. Which then it would be a great.
Yeah. Is that okay? Yeah, okay. So astrobiologist Jeffrey Marlowe, he was like one of the co-research man on this. sorry. It was an important guy on this research, right, in this experiment. He said if these types of rocks are under the ice making oxygen, that could allow a more productive biosphere to exist. If photosynthesis isn't required to make oxygen, then other planets with oceans and metal-rich rocks could sustain more advanced life than we've thought possible. So basically, oxygen-producing rocks on alien worlds could mean alien life. And that's where like the conclusion's made. The link's made. Right. So the deep ocean is basically more alive than we've thought, right? For years, scientists have assumed that the deep sea was just a graveyard of like sinking dead material and just barren and everything, right? yeah, basically a place where like life scraped by on leftovers. But now with discoveries like the hydrothermal vents, which Aldona knows quite a bit about, which let me finish the sentence and then she can get to it. Hydrothermal vents, or like methane seeps, which are basically just natural gas leaks under the ocean, and ad hoc oxygen. These suggest the deep ocean is way more active than we've ever imagined. Do you want to explain what hydrothermal vents are?
I don't know if this is accurate, but this comes from Octonauts. It's that episode where Captain Barnacles he goes and visits the Mariana.
Yeah.
And he finds like these little volcano-looking things, and then he decides to like bring one back home with him. I don't even know why. And he decides to like chip away at it, and he finds like this little like glowing green worm in it, and it's been living in the hydrothermal vent because it's like lots of high pressure, lots of high temperature, but it couldn't survive in a submarine. Humans can't. I mean, like, they're not humans. They're like Octonauts. Oh no, wait.
Worms.
Worms. So why is it called Octonauts?
That's just the show's name.
Like their logo is an
No,
octopus.
that's
The ship
deceiving.
is an octopus shape. No, yeah, the ship
Yeah,
is an
yeah,
octopus.
Apollo basically sums it up saying that it helps us to see the deep ocean as a place of production, which I think is a fun inversion of how we tend to think about the deep sea. So the takeaway, the deep sea is still fun, is still full of fun surprises, and we might just be scratching the surface of what's actually really happening down there, and we don't know what's happening down. Like there's so many things that we don't know. But yeah, this is only one of the many recent discoveries that we've made about 5% of the ocean. And yeah, to be fair, I'm looking forward to like us finding out more cool stuff like this. And yeah, that's it.
Wait, so
That's so cool.
when was this discovered?
This was discovered towards the end of last year. Like it's quite a recent. Okay, don't quote me on this, but like I want to say around 2024. So it's quite a recent discovery. Like it's not like been out there for years. But yeah,
Thank you.
So, like deep sea mining, what are they planning to do with it?
okay, because so there's minerals down there such as like iron, nickel, cobalt, and like manganese and whatever. And those are basically we can use them for like renewable energy. Like you know how we like need all the batteries and minerals like for our energy stuff, right? They're basically just mining them to get the minerals so we can like because it would speed up our use of renewable energy. So like it's quite double edged because some people say we should be mining more so we can move towards renewable energy, which is good for like the greater good of like the world and everything. But some people are like, you could be stripping away the animals that live down there of their survival. So it's just like a double edged thing of like, do we do this? Do we not do this?
Right, so with this information, we can like dominate COP26 or COP27. Like
With what information?
as in like new renewable resources. We don't have to stick to sunlight anymore.
See, maybe. See, this is where it's like interesting, like, because we've genuinely just thought up until now you need sunlight to make oxygen. It's just like you could technically, and I mean, in the later years, in the future, you never know what we're using.
So poorer countries.
Technically, yeah, they could, or places that have like lack of sunlight because they're like quite, crowded. I'm not crowded, but like they're covered up. We could technically use them.
So England doesn't need to spend much money on sunlight, so there's no sunlight.
Maybe.
England mainly uses
Did you
wind.
microphone?
Doesn't England mainly use wind turbines anyway?
There's not that much wind except for beaches.
There's lots of wind. We're in England all the time. How you just seen outside?
Windy, but is it enough to turn a wind turbine?
I don't know. There are wind turbines kind of everywhere.
I feel like if any country has enough wind,
Yeah, it's probably England. England owns the wind at this point. Yeah, which is unfortunate. Well, it is what it is.
Yeah, no, I'm done. That's basically all I had to talk about today. So I hope you guys enjoyed that bit. Yeah. Thank you.
Okay, so I'm going to talk about Euclid, who is the father of geometry. And I'm going to explain some of his works, his theorems, and what it's led to, and just what it means. So Euclid was an ancient Greek mathematician, I think in around like 300 BC, and he is known as the father of geometry because he made these 13 books called Euclid's Elements, and it consisted basically everything there was to geometry at that point. So he used these things called like postulates and axioms, which are just like the basic facts in geometry that are used to explain reasoning for more complex ideas. So he started with these 5 postulates, and they are the basics. So I'll explain what they are. The first one is that like if you have 2 points, you can draw a line between them. A straight line, it's the shortest distance between 2 points. The other one, so lines can be extended indefinitely. They can go on to infinity. Another one is that any line can be the radius of a circle. Sorry, can you see?
I can see.
And the fourth one is that all right angles are equal. We know they're all 90 degrees. But the fifth postulate, so it caused a lot of problems because it is basically that parallel lines never meet. So what he said was that if you have like two lines and a transversal, which is a line going through them, and if the co-interior angles, if they add up to less than two right angles, so if they add up to less than 180 degrees, then they will meet at some point. Like, they are going to meet if you extend them. It's inevitable. And if they are above 180 degrees, then so like this side, they will just kind of go in the other direction. So basically, they will meet if they add up to less than 90 degrees. That's all that the parallel postulate was saying. But for centuries, mathematicians were like, oh, this is a lot more wordier than the other four. How can we prove this? So they were working on ways to prove it. They were like, they tried rewording it and using proof by contradiction. And I will get onto the whole thing that the fifth parallel postulate led on to. But first, I'm going to explain some of Euclid's proofs. So I'm going to explain how he geometrically proved Pythagoras' theorem. All right. So if you have a right angle, this pen is like showing it up. So if you have a right angle triangle, he wanted to prove that so Pythagoras' theorem is basically saying that these two squares, adding the area, should add up to this area, because the two squares should make the square of the hypotenuse. So he proved it geometrically. Okay, so he drew some lines, and using all of his axioms and postulates, the 5 postulates that I spoke about, he was able to prove how this is true. So one thing he said first was this triangle. Horrible, oh my god.
It's alright, don't worry.
So one thing is that he wanted to prove that this triangle is equal to this triangle. Because, well, I should have said this. He wanted to prove that this square was equal to this rectangle, and this square was equal to this rectangle, and that would prove his point. So first he wanted to prove that these two triangles were equal. So using his other axioms, which are just like just facts in geometry, he proved that these two triangles are equal, they're congruent, because they share the same side. So like because this is a square, this side is equal to this side. So they have the same side here, they have the same side here, because this one is equal to this one. So they have two of the same sides, and well, since these are right angles and they share this angle, so this angle and they're two right angles, that means that this angle is equal to this angle. So using the fact that the side angle and side were equal of the two triangles, he was able to prove that they're congruent. So that was the first step of proving this theorem. The next was that he wanted to prove that this square was equal to two of these triangles. So let's just redraw this. So this is just this picture here. So you've got the square and you've got the triangle. So this is just, this line is this straight line. These are parallel lines, as we know. And he wanted to prove that the area of the square was equal to two of these triangles. I hope you guys can see that. It might be a bit small, but so the area of this is a parallelogram, a square. It's a type of parallelogram. The area of parallelogram is the base times height. So let's say the base is x and the height, we'll call it h. So the area of the square is xh. And we can find the area of this triangle by extending this and drawing a line. Now we have another parallel. So let's extend this to x. So all of this is equal to x, and so is this. So the base and the top is equal to x. So the area of this whole parallelogram that we've just drawn is going to be the same as this, because you've got the base is x and the height is h. And the triangle that we had originally is half of this parallelogram. So if the whole parallelograms are equal, yeah, and the triangle should equal, because it's half this parallelogram, it's half of this. So he proved that this square is equal to half of this triangle. And the same can go over here with this rectangle and that triangle, because you can do the same thing. You can extend this line, and you can draw that. It looks nice. The same thing applies. So what he was able to prove was that this square is equal to 2 of these triangles, and this rectangle is equal to 2 of these triangles. And since the triangles are the same, he was able to prove that this square is equal to this rectangle, and it's bilateral. So we can do the same thing on this side. This square, I'm not going to explain the proof again, but I'm sure you could try it on your own. Got to keep the microphone. So the square is equal to this rectangle, and through this he was able to prove that the sum of these equals this triangle, this square. So that was his geometrical proof of Pythagoras. And yeah, another thing that he was able to prove was infinite primes.
Wait, I have a quick question.
Oh yeah.
Why did Euclid want to prove
Well, so Pythagoras had his theorem, but like it's not really valid unless it's really explained.
Yeah.
So
Wait, so did Euclid prove Pythagoras' theorem, so then it was like finalized, or did Pythagoras already like prove it, and then he was just like going off on it to prove his postulates?
I don't think Pythagoras really had like, I don't think he explained his proof well enough.
Oh, okay.
Or if he did, at least,
Is it not?
I'm not really sure. Probably not, but he might have used algebra didn't exist back then, so this geometrical proof, I'm assuming this was the first proof I'm gonna talk about later. It's like, so there's this explanation of hyperbolic geometry, which I'm gonna go through, but it was also like, so we've got like one mathematician who's discovered it, but also a few others have discovered it, but it wasn't really recognized until like later. Like this one guy, Lobachevsky, he discovered it but he wrote his work in Russian, so no one's gonna translate it from Russian.
There we go.
So they just kind of kept it.
That's so unfair.
I know.
Also, at the same time, I feel like because all the sciences and maths, it's not very individualistic. It's very like it's teamwork. It's like putting different ideas. So it might be like, I feel like maths is kind of a conversation that keeps going through the centuries, almost as like philosophy. It's like a long conversation. Like people come up with proofs even centuries after. So, like, also on these things, don't really like on these segments. Don't quote us because we are teenagers. We are 17-year-olds, and we're not actual mathematicians or anything. So please don't
We're
quote
just
us.
doing our best.
Can we
Yeah.
put like a little
A little
disclaimer?
Disclaimer, yeah.
Yeah, but no one's quoting us, so.
So another proof I'm gonna go through is the proof of infinite primes.
Oh, I like this one.
Yeah. So I'm gonna. Well, yeah. So Euclid, he defined primes as measured by a unit alone. That was in his book, Elements, and he made a lemma, and it was that. So if you have AB, which is a natural number, and factors are like A and B, so they multiply to make AB. And if you have a prime number, let's call it P, and if P divides AB like exactly, then his lemma states that it should also divide A or B. So at least one of them it will also go into. So like let's say you have 63 and two factors can be 21 and 3. So prime number 7 goes into 63 and it should also go into at least one of these, 21, and so that should work for everything. And this led to the fundamental theorem of arithmetic, which it states that every number greater than 1 is a prime, or it's equal to, or it's like made of a bunch of primes, so it's the product of primes. So this was used in his proof of infinite primes. So this is his proof. So he used, this is not his proof because algebra did not exist in his time. So this is just an elegant proof of infinite primes in an algebraic way. So let's say the statement is that primes can go on forever, and we're going to use proof by contradiction. So we're going to say, no, they can't. You can actually write them in a finite list, and you can like write a complete list of primes. So let's go like 2, 3, 5, 7, 11, 13, and we'll go on up until n. Let's say this is our finite list of primes, and we're going to make a number. We're going to make a number, and it's going to be 2 times 3 times 5 times 7 times 11 times 13 times everything up until n plus 1. So this new number is made by multiplying all of these primes and adding 1. So either this number could be prime or it isn't prime due to the fundamental theorem of arithmetic. So if it's prime, then we add it onto this list. It's a new prime, not on this list. That already proves it wrong. So it's a new prime that is not on this list, meaning that this isn't the complete list. You could repeat the process and find more primes, and it proves that they go on for infinity. But if it's not prime, because we don't know that it's prime for sure, well, the fundamental theorem of arithmetic says that it is made of multiplying primes together. And it can't be made by multiplying any, so it can't be made by multiplying any of these, because none of these numbers are going to divide this number perfectly. 2 will not go into it because you'll have a remainder of 1. 3 won't go into it, you'll have a remainder of 1. So none of these numbers on our prime list will go into this, meaning it must be made of another prime, which is not on the list. So that proves that this list is not complete. So by contradiction, we know that we could repeat the process again and again, and primes go on forever.
That's my favorite proof. It doesn't require much.
Yeah, it's pretty elegant. That's what mathematicians call it. So, yeah. So that's some of his proofs. But now I'm gonna explain, like I was saying earlier. So, the fifth parallel postulate. So mathematicians for centuries, they were trying to find proof for it, because no way, like his other 4 postulates are you can draw a line, all right angles are the same, like they seem straightforward. So they reworded it into this: you can have a line and a point that's not on the line, and you can only draw one line that goes through it and is parallel. Only one line that will never touch this one and goes to that point. So that's the 5th postulate reworded.
Wait. I have a question.
Yeah.
Why can't you draw another line that would go through at the same place, but would be parallel as well?
Because like any other line you drew,
Like if you had another line, like if like okay wait, you had another line over here, like just there, wouldn't that also be parallel?
What, here?
Yeah, like through the point.
No, that's the line Amy drew.
No, like if you have, wait, no, I don't want to go over your work, but if it was just like another, like going through here, like there,
It's the same line.
but like wouldn't it be 2 different lines? Like
Okay, even if it was a bit lower,
yeah,
it might change the cointerior angle, so it might not be parallel. Like there must be only one line that goes through it.
And like,
right, that makes sense.
So the term parallel, we're gonna say, sorry. So parallel, we're saying that you can extend it indefinitely and it will never touch. So that's what we're saying parallel means. So mathematicians, they tried proof by contradiction, and they couldn't do it until this one mathematician, Bolyai. He 2000 years later, after Euclid made his postulates, he proved, because he thought about what if it was like curved. So this led to non-Euclidean geometry, and a quote from him is that out of nothing I have created a strange universe, which is non-Euclidean geometry. It wasn't only him, there was also like Gauss and Lobachevsky, I said earlier. They also wrote about this non-Euclidean geometry, but were not as recognized. But credit to all of them. So I'm gonna explain what it is. So non-Euclidean geometry it's different to, as we know, Euclidean geometry is just like 2D squares, triangles. It's basically where the fifth postulate doesn't hold up. So that means you cannot draw only one straight line through that point that is parallel. So one example of non-Euclidean geometry is spheres. So if you have a sphere, then so let's say you have a sphere and you have 2 points and you want to draw a line that is the shortest distance between them. That's called geodesic. When it's geodesic, it's the shortest distance between 2 points. So you draw a line, and it's actually going to be the shortest distance between 2 points on a sphere it's a segment of what's called a great circle. And a great circle is basically, imagine a sphere and it just goes around the whole thing, around the whole diameter. So it would cut the sphere into half if it was a plane. It just goes around the whole diameter, and the shortest distance between 2 points is going to be a segment of a great circle. So if you kept going from the 2 points, if you kept going on this short path, you'd make a great circle. And if you had another 2 points and you drew a line, you draw the full great circle, they will always intersect. So on a sphere, lines, if you have a line at a point that is not on the line, you can draw as many lines as you want, but they will always intersect. Great circles are always going to intersect. So this is non-Euclidean because the fifth postulate, that you can only draw one parallel line, it doesn't hold up because you can draw 0. You cannot draw 1. They'll always intersect. So yeah. And a thing about spherical geometry is that like it might look curved. So a straight line, it might look curved. You might think, oh, how is that the shortest distance? Because let's say if you had a map and you flattened it out, so let's say a plane flew from one country to another, and you flattened out its path on a map, it would look curved, but that's just the perspective you're looking at it from, because really it is the shortest distance. So in this Euclidean geometry, it is all the regular rules of. So if you had a sphere and a triangle, you drew a triangle on it, all of the sides, all of the angles, they would add up to more than 180 degrees, because non-Euclidean geometry, it's different to the regular geometry, and the sides would look curved, but they are actually the shortest distance between 2 points. So yeah, that's spherical geometry, which is non-Euclidean, and there's also hyperbolic geometry. So I did make a piece of hyperbolic crochet because I found out like all the research I did, and then people were just pulling out the hyperbolic crochet, and I'm like, oh, I can do crochet, I'll do that. So hyperbolic crochet, I mean geometry. So hyperbolic geometry is when you have, it's a non-Euclidean, it's curved and it's growing exponentially, the curves. So it's like so the fifth postulate does not hold up, because let's say in this crochet you drew a line that could go just straight through it, one straight line, and you had a point that's not on the line. You want to see how many lines you can draw that are gonna go through that point and not touch the original line, so that it proves see how the fifth postulate holds up. And the thing is, you can actually draw infinite lines that go through it, because if you drew a line and it looks straight, okay, because if you like flatten this out and drew a line, it would look straight, but when you let it curve up, it's like it doesn't look straight. So it really just depends on the perspective you're looking at it. But in hyperbolic space, the shortest distance between 2 points, geodesic lines, they can look curved. So it just depends on the perspective. So in hyperbolic space, you can draw infinite lines. So the fifth postulate doesn't hold up because you can draw infinite. So this, I'm gonna draw an example of Poincaré's disk model. So it's an example of hyperbolic space. It's just gonna represent a boundary because really the Poincaré disk, it goes on forever. Hyperbolic geometry, it goes on forever. It's infinite. So we're just gonna pretend that's a boundary, and you can draw like a straight line that goes through it, and if you have a point that's not on this line, well, you can actually draw infinite. So the thing is, lines.
I thought it had to be straight lines. It doesn't matter if they're straight lines or not.
Well, this is actually a straight line, but it like depends on the
because
perspective
of this
you're looking at.
perspective.
So like,
okay.
so like here, you could draw a straight line, but it's gonna look curved once it curves up.
Right. Okay.
What's perspective? Like, what do you mean by it depends on perspective?
Like,
Is it like the space-time curvature?
yeah, I'm gonna talk about it later on, briefly, but
Are these right angles?
yeah. So the thing is that straight lines, the shortest distance, so geodesic lines, the shortest distance between 2 points, in the Poincaré disk, it's gonna be an arc of a circle with an infinite radius because it goes on forever, and they're going to be at right angles to the boundary, and that is the shortest distance. So again, it depends on the perspective you're looking at it, but from this perspective, that is one line. You can draw many, and as long as it's perpendicular to the boundary. The point is though, you can draw many lines that go to this point. You can draw infinite lines, and it won't ever touch because it's curved, and that's hyperbolic space. And yeah, it's growing. So like this crochet is just a small piece because I did not have much time, but it is growing exponentially. These like ripples. So it's another form of non-Euclidean geometry, and it's actually the opposite of the sphere. So in the sphere, you can have 0 parallel lines, but here you can have infinite lines. They'll never touch. If you draw them that way, they won't ever touch. And the whole thing about spheres, if you drew a triangle on a sphere, it would have the angles add up to more than 180. In hyperbolic space, they add up to less than 180 because like it's curved. Distance in hyperbolic space, it's different. So what might look like, because you might see this and think, the shortest distance between like, let's say these 2 points. Well, let me draw it. The shortest distance between like these 2 points, surely it's just going to be like that, and that should be the shortest line, right? But actually, since this boundary is actually infinite, you're walking millions and millions of miles to get here. So actually, the shortest line is going to be like that. But again, our perspective is different. So it's at right angles. That is the shortest line. Distance is different in non-Euclidean space, and this actually helped. So Einstein and his theory of relativity. Don't trust me too much because I didn't look into this too much because it's like physics. I don't want to be overstepping. And
Please do.
no, okay. And he used non-Euclidean geometry to describe how the space-time curvature it's hyperbolic. So he used it to describe how gravity works. So if you have objects in space, so space-time is hyperbolically curved. Two objects, if you have an object, it's moving in a geodesic manner in space, and gravity also works. So it looks like it's moving in a curved path, but that is the shortest distance due to the negative curvature of a hyperbolic space, and it helps to understand how gravity works. But yeah, so Euclid was able to help mathematicians think about the geometry of spheres and hyperbolic space, and just because of his fifth postulate, sometimes mathematicians were like thinking, did Euclid know what he was doing when he wrote like one simple postulate and it opened up new universes? but it did have a good, like, it was quite useful in like thinking about how the globe, how like planes will travel in the shortest path, and how gravity works in space-time curvature. And yeah, it's thanks to Euclid. So I hope you enjoyed some of his proofs and explanation. I tried my best of the non-Euclidean. It's really hard to explain.
No,
so
you explained it really well.
yeah.
Okay, so my topic is about personalized medicine and the possible dangers of it. So, personalized medicine is using your own genetic data to create treatments that are specific to us. So, it only works on us, it doesn't work on anybody else. But the problem is, what if that same technology could be weaponized? So, a virus could be decided to target just one person or a group of like ethnic people or.
Not us being targeted again.
So, how it works is like each person has unique proteins on their cell surfaces, and it's dictated by their DNA. And obviously, no two people have the same DNA, except for twins, do they?
No, I don't think so.
I don't. And these are the antigens that your body recognizes as self. So anything other than that is non-self, as in you just start attacking. So the theory is that engineers, or genetic engineers, they could design a virus that only binds to those specific proteins. So it would infect one person, and everybody else would be unharmed because people don't have the same DNA. I think, yeah.
Well, we're still not quite sure.
No.
Bit of a grey area.
Okay, so first you'll need access to genetic data, like we've discussed, so from like ancestry.com that people can easily hack. Then you would need to analyze the genome for unique weaknesses, like mutations or a person, or like something that makes.
What? It's just now. Are you giving an instructions on how to?
As in like a fun fact for like educational purposes.
You're just talking about how lethal this is, and then step by step.
No, but it's not like I'm not giving specific instructions. It's just like the general idea of what you would need to do.
Okay.
But
Yeah, if like you must have gotten this from somewhere. I'm sure like if it was specific enough, people would have already done this. And
yeah. I'm not encouraging this, obviously. But like,
Also, because I don't think any of our viewers is the target audience.
I'd like to know a step by step process.
Yeah, please do continue. Sorry for the interruption.
okay. So access to our genetic data, that's step one. Which you can just hack into like websites, ancestry.com. They probably don't trust those websites completely.
Ancestry.com is never going to sponsor us. That's one off the list.
And then you need to analyze their genome for specific weaknesses, as in like, you know how some people are more likely to get a disease than others. Mm-hmm. So like, I think it's breast cancer that they've recently found out that it might actually be a genetic thing.
Yeah.
As in like, some people are just born with a gene that just makes it more likely. So if you learn about these things about people, like on like a really, really deeper level, then you can like exploit these weaknesses. So then what you would do is you need to design a virus or a toxin that exploits these weaknesses. So you could do this using CRISPR technology.
Oh.
Yeah. Which is what I've been obsessed with recently. What is it? Not for these purposes, obviously, but like
just for me and Amy who don't do biology or CRISPR technology.
CRISPR technology, it's this thing. It's basically scientists have like seen this process that happens in bacteria. So CRISPR actually happens naturally in bacteria, I think, from what I read. It's like the process is like if you cut the bacteria, you leave a gap in their DNA, and before that DNA can sort of be rebuilt, there's like a little gap, and in that gap you can put in whatever you want to put in. So then when it does like eventually like reform, regenerate, heal, that whatever you put in, that will also be reformed with it. So you need to utilize that gap and do whatever you want to do.
Okay, thank you.
Then you'd use CRISPR technology to like actually make the virus. So you can maybe get like an existing virus, like split its DNA, add some extra things in if you want to, that sort of stuff. Or like add some of like oh, I've got an idea. No, I've just been like,
Okay, go on.
if you get, I'm not sure if this would work though, but like, if you would get like, because obviously like these, you would want the immune system to not work, but the immune system only attacks things that are non-self, that have antigens that are different to themselves. So if you could like use the body's self antigens, input that into the virus, so the body would think that the virus is actually self.
Oh, that's smart.
It's like how HIV works. How like HIV, when it like bursts out, it uses the cell's own antigens. So that's why HIV is really hard to treat, because the body thinks that HIV is actually a part of them. Because when they see the antigens, oh, it's self. I don't have to do anything. I don't need to create antibodies or anything. The HIV is just running around the body like completely wrecking it.
That's actually so smart.
So if you could put self antigens into a virus that you engineered, technically, once that goes back into the person, your body is completely defenseless, because your immune system is like, oh, that's just my antigen. It belongs in my body. I don't have to do anything. But that pathogen is just going to be like accumulating, reproducing, and just bam, just attacking the person. And the immune system wouldn't even realize. Theoretically, obviously. It was just like an idea I just had right now.
Okay.
And then the last step, which is the most important step, how would you deliver it? Because it's good that, no, it's not good. You've created this, but now if you were to deliver it, how would you deliver it? So I suppose it wouldn't really matter how you deliver it, because it could only affect the person that you're targeting. So you could put it in food, or maybe even have it as an airborne pathogen. Wait, so sorry, Siri just keeps acting up. It isn't just a modern thing. So back in the Cold War, the Soviet Union's biopreparat program, I don't know what that means, reportedly explored ethnic-specific biological warfare. So if there is a specific ethnic group you don't like, you just wipe them out. Okay.
Oh.
Did that answer your question?
Yeah.
What was it?
No, I was just gonna ask you, what do you mean by specific ethnic groups? And then you answered that you just wipe them out if you don't like. Okay.
Yeah.
So technically, if technology was advanced as it is now, I feel like you guys know. I feel like you guys know where I'm going. If it was advanced as now, as it was back then, like Hitler's time, could he technically have used this, like wipe out?
Oh, he would have 100%.
Wait, what would he have done?
Like wipe out the Jews? Like would he? Like
I
is this like something that you can do?
Probably, but I'm not sure. Like, I'm not sure. The thing I'm not sure about is like, I don't get where the ethnic group comes into like having similar DNA.
Yeah, I was just gonna ask you, how does that correlate? Because like we might have like similar codings and stuff. Like, isn't like a blood like you know how like Asians like have iron deficiency, right? Like that's like
I thought it was just. I thought it was like
most do. But like, is that how it would correlate? Like,
Surely there is DNA related
Yeah,
to
exactly.
I feel like it would. I mean, I feel like some parts will be the same, as in like skin color, like the genes that code for skin color. Hair
so then you would target those specific ones and like use it to like. Interesting. Okay, thank you.
I bet that might be it, though I'm not sure. But the thing is, if governments are even like considering the idea of manipulating genetic data, what does it mean in the future? Because like, you know, like ancestry.com and those type of things, and we trust them, we send them like a sample. I don't know how they do it. It's like spit. What is it?
I think it's just spit in a cute transparent thing.
Yeah.
I want to say you spit in it.
As in, like, lots of people think of it as a joke. As in, like, well, they don't consider it that serious. They just spit and they tell you, oh, turns out you're related to like a queen or a king, you're actually royalty, or you're like, yeah.
Yeah.
But do you really trust those companies to not sell your information?
Mm-hmm.
Should genetic databases be banned? Should governments develop defensive biotechnologies? Like, should it all be a thing? I feel like that's the problem with personalized medicine, because although it's like such a big step in like medicine and technology, there's so many things that could go wrong with it. That's why it's not something that's used worldwide. Because I feel like in this case, the negatives do outweigh the positives a lot. But if we could overcome that, it would be absolutely amazing. So to end off, are genetic bioweapons inevitable, or are we just being paranoid? Should we embrace personalized medicine despite its risks? Or can we use personalized medicine, but we just put in stricter rules? And yeah, that's it.
So I'm gonna be talking about Fermi's paradox, and I think the question that we should start with is, what is a paradox? So a paradox is when you begin with a set of self-evident premises, and then from them you deduce a conclusion that then undermines them. So where did this come from? So in the spring and summer of 1950, it saw the disappearance of trash cans in New York City. It was also the year of flying saucers, or like, people saw flying saucers. And there was this like little cartoon in a newspaper which depicted aliens taking trash cans back home, which I think it was cute. And then that sparked a conversation with Enrico Fermi and his colleagues, a lunchtime conversation. And then he asked everyone, where is everybody? And from then, Enrico Fermi's paradox. So for context, Enrico Fermi is an Italian physicist and arguably one of the most important physicists in the 20th century, and he was the father of nuclear physics as well. The question is not that extraterrestrial intelligence, and because that is so long to say, I will just shorten it down to ETC, so extraterrestrial civilizations. It's not the question that if they do exist, rather that we see no evidence of them existing, especially because of the principle of mediocrity. Our sun is a relatively young sun, and there are older stars out there, and our Earth is nothing special either, because there are other planets that are in the habitable zone in other solar systems. And technically, after millions of years, an alien civilization would likely have the technology to then go out of its own planet. For example, in 100 years, we went from like covered wagons to landing on the moon. And, we might go and colonize the galaxy in the future, but I don't think we'll be alive for it. I'm not quite sure we will be. So an interesting equation that comes from it, that I will be now writing on the whiteboard if I can, is Drake's equation. So Drake came up with it. Oh! Did anything happen?
Drake.
No, God, not the singer, Drake. The physicist, God. Anyway.
Clarifying it out.
Yeah. So it says that n being the number of communicating ETCs in the galaxy can be determined by R, which is the yearly rate of star transformation, or star formation, times by Fp, which is the fraction of stars that have planets, times Ne, which is planets that have an environment suitable for life, times Fl, which is fractional planets that can support life, times Fe and Fc and L. Wow, that's a horrible one. But Fe being planets that support life that then can go and develop intelligent life, times by fractional planets that will have civilization that will devote their time to communicate with us, or like with any other ETCs. And then L being the years that they will try to communicate for. So I think we're going to be quite positive with these numbers. Yeah.
How do you find out like each individual one? Like how do you find out which planet will be able to communicate with us and want to communicate with us? Or
I think
how do you do that?
we don't. We're just being. It's like it's an estimate.
Okay.
So in this case, we're gonna be really positive with it. There's a online calculator that you can choose. You know the numbers you want to put in. But for now, we're gonna be positive.
What do you mean by they want to communicate with us?
Okay. Because there might be some ETCs. I'm gonna be talking about this in the dark forest theory, but there might be some that are not willing to communicate with others. Like we put ourselves out there in search for life, but there might be some that just want to stay silent.
But how, if they do want to communicate, how would they communicate with us?
Oh, I can get later. I get on like how we try to communicate, but um an example of like communication, which might have not been a communication, was there was a wow signal in the August of like 77, and it was um this I think it was a long and intense blast at a specific frequency that came from the Sagittarius area, and people thought that it was aliens trying to signal with us. Other people thought it was just a cloud of hydrogen that has been hit by radiation. And we did try to reply to that in 2012 by trying to by beaming a response in the same region. But I think it just proves how long it takes to communicate between, because we send that signal 30-40 years after the signal reached us. And also it might just not be an alien signal, but
like in these signals, is it just sound or is it like words incorporated? Like can
like
you,
a
send like a message or they understand or
I'm not quite sure. I suppose that the only thing you can send is frequencies, and then you can. Sorry.
like interpret frequencies?
But the thing is, though, if they're sending frequencies to us, they'll have enough technology to be able to decode ours. Like the way that we're able to send them out, because they'll be more advanced than us if they're able to send one out to us. Like because they'll be able to see, oh, there's a planet out there, and we should try and reach them. So I think that they would only be able to send one out knowing that they can decode one themselves. Like I don't know if that makes sense, but like that's how it works in my head.
So there could be life that are more intelligent than us.
Yeah,
Definitely. I hope so. I would hope so, because have you seen humans? I mean, it's just the possibility that we're the most intelligent life out there, especially because in the Milky Way alone, there's only 100 billion to 1 trillion
But
stars,
what does it mean by
and that's a lot.
intelligent life?
Life that can communicate or is.
So what would be considered more intelligent than humans? Like what qualities would they have that we don't have?
They're more advanced.
Yeah, they might just have better technology than us. I was just thinking that. Yeah, they might.
Like the way that it's like 100 200 years ago compared to then, we're a more intelligent species. Like so they would just be more advanced. Like they could have like, I don't know, flying cars.
We create not like our own physical ability.
I mean, for all we know, like they could have different, like telepathy. Like that would be a physical ability they'd have. Like that wouldn't be like man-made, like created. Like for all we know, they could like have you seen Avatar and how like they attach their tails and communicate? Like like it could be intelligent anyway. Sorry, I'm taking over. Like sorry, this is your
That's
topic.
fine, please do. I love that. I love that.
Do you say it's a good idea to always communicate?
Do you guys want me to go over the? I'll finish this,
Yeah.
and then I'll get to the dark forest hypothesis, and then you can get me back on that. Yeah. Okay. So we can be very optimistic about this Drake's equation that with these numbers again, people usually are not. But okay. So R can be 1, so 1 star can form per year. And then we can have half, so for every star that forms, there's a 50% probability of it that has planets around it. And then the number of planets that have an environment for life can be 2. So, planets are in the habitable zone. And we can choose 1, so for every planet that can develop life, it will develop life for sure. And we can have we can have 1 for every life that will be developed will be intelligent life, and we can have 1/10, so 10% of that life developed will want to communicate with us or with any other ETCs in the galaxy, and we can have L as 10 to the 6. So that intelligent species will try to communicate with us for this many years, and that comes to this. So our estimate of ETCs in the galaxy is around there. But then again, we are being very optimistic with what? We are being very optimistic with these numbers because I was just digging online, and if you input certain numbers, you only get like 12,000. So I think this is wildly optimistic.
So, is there any evidence to back up where they got these numbers from?
No, it's just an estimate. Like we're just hoping that for every star that will form, at least 50% will have planets, and that for every life that forms, that life will be intelligent. We're just hoping. We're just assuming that it will be, and also we're just assuming that only 10% of life will want to communicate with us. It could be just 1%. Again, this is very optimistic numbers that I just input into this Drake equation. Hilarious Drake equation. So we can go back on the dark forest hypothesis. So one of the solutions to Fermi's paradox is the conjecture, which is an opinion based on insufficient evidence. It's a dark forest hypothesis. So if you imagine yourself in a dark forest where trees hinder the light coming from the moon, from the stars, and there's no light around you, or darkness is surrounding you, you cannot possibly light up a torch. You wouldn't dare to light up a torch because lighting up a torch would mean that you're giving your position away to someone that might be in the same forest, so a predator in the forest. Of course, you don't know if there are predators in the forest, but so if there are not predators, then you would be safe. But if there are, you just gave your position away. So that might be the same thing for ETCs. So maybe some ETCs are staying silent because they are scared of like other hostile ETCs around the galaxy. Dark forest hypothesis is quite concerning. Very interesting. Because I think it is the one that makes more sense.
How's that concerning?
Because we literally just like with all the signals we try to send out, and I will get onto that. We're just giving our position away.
Mm-hmm. Has there been like problems about it? As in because we've obviously sent signals.
Yeah.
Has anyone reached back out to us in a negative way?
And no one has reached. That would make the news. But I think that's mainly because of time. Like it's very recent, and it will take maybe even millions of years for us to receive a response.
Where are they sending signals to?
So like the wow signal, they beamed it to the same part of the Sagittarius. But yeah, I'm sorry, interruptions. Another solution to Fermi. Are you okay? Yeah. Another solution to Fermi's paradox is the zoo scenario. So an important question when we're thinking about ETCs is on how they will exert their power. So if we think about an analogy from mankind on how we exert our power is through like keeping wildlife in sanctuaries or like in zoos. That's how we exert our power in nature. So some people think that, I don't know where I was, but to recap, we might be the animals in the zoo for the aliens, and I think a more obscure or terrifying hypothesis is the fact that we might be lab rats in a laboratory for aliens. Although I do have to admit that's not the best hypothesis, because it would imply that all ETCs are collaborating on this, which, I mean, if we think about humans, we don't collaborate on things, so it's kind of hard for like other aliens to collaborate. That seems silly. The solution is a great filter, which is an idea developed by Robin Hanson, who also did a TED Talk, so if you want to check that out, that would be great. And he thinks that the development of civilization that can colonize a galaxy is unique, just maybe once in a lifetime of the universe event, mainly because of the many barriers or filters that the civilization has to go through. So he has like 9 steps, and the first one is having the right star system, reproductive something, so like RNA, things that needs to reproduce. Single life cells, complex life cells, so eukaryotic single life cells, sexual reproduction, multicellular life, animals, and where we are right now, that's also a filter. And the 9th step is colonization of galaxies, of course, because we already reached colonization here. So what he says is that passing these filters might be more uncommon than we think, and we might be one of the only civilization that has passed such filters and that has, reached this level. So filters that we already passed is like, going from just condensed matter to multicellular life. That's a filter we might have passed, and upcoming filters might be AI development or the development of nuclear weapons, because nuclear weapons supposedly should lead to a nuclear apocalypse where our civilization would be wiped out.
Biological warfare as well.
Yeah, that might also be a filter. That would make sense. In the sense that the civilization might kill itself before we pass through another filter.
Wait, do you want to explain what a filter is to the audience?
See, I wish I knew myself. I think the filter is like a step into the development, and some civilization might be stopped at a certain development that would make them less intelligent than
like a stage.
what we are.
Yeah.
So I would have another paradox, but we can go over that, because it's not that important. But a fun fact is, one scientist estimated the probability of picking a set of random parameters that will generate this life and the favorable conditions of this universe that then led us to intelligent life like us. And the chance is 1 in 10 to the power of 229, according to him. Which is basically, if you think of the UK lottery, and if the chances are 13 million, if it's 1 in 13 million, and if the draw happens every second, so there have been 10 to the power of 17 draws till now, but only because the creator of the lottery are miserable human beings, or just beings, only 1 draw in 10 to the power of 17 will actually win such prize, then I think it's just a crazy estimate of like, the random parameters just aligning together. But then again, we don't know about the existence of God, and I'm not here to be a religious speaker. So have we tried any contact with aliens? I'm gonna wrap this up quickly because I think my phone might be dying. So have we tried any contact with aliens? Not necessarily specifically, at least not what I'm gonna talk about. So the Pioneer plaques, we sent them with Pioneer 10 and Pioneer 11, which were the first spacecrafts to exit our solar system. And these plaques contained engraved messages, and one was the hydrogen atom, which is, you know, the symbol of physics. Unused of a male and a female. Our solar, like our cosmic address, so like our position in the solar system, and the path that then Pioneer would take. Unfortunately, we don't know where Pioneer 10 is anymore because we lost contact in the first half of 2023, and at that point it was 7.5 billion miles away from now. So we don't know where it went. Like it might have reached somewhere. It might have reached some ETCs. They have just some nudes of males and females, which is great. But we also have the Voyager golden records in 1977, so Voyager 1 and Voyager 2, and it's just a gold-plated photograph record that contains a greeting in 55 languages, contains about 116 images of animals, humans, and plants. It also contains 90 minutes of Bach and Beethoven and other traditional music. It contains sounds, so like animal sounds, and, you know, it's just the water. And yeah, and we also have included instruction on how to play it, and our address, our cosmic address, it's included on there. And Voyager 1 currently is the farthest spacecraft out there. It's around 2.5 times 10 to the power of 10 kilometers away.
So we still have contact with it?
We still have contact with it. And then like, yeah, I think we do. And that is the furthest away, and it's in the Ophiuchus era. So the odds of, you know, alien civilization finding them are very slim, but you know, they're like a symbol of like a kind of time capsule of humanity. I think that's so cute. That's so cute of us. We're so cute sometimes. But other than that, I think that's about it. That's about Enrico Fermi's paradox and a few solutions to it, and just aliens. What do you guys think?
I genuinely think the way we've tried contacting other aliens out there is like the coolest thing ever, because like imagine being like an ETC and being able to crack the code, and then like seeing like things that we may have, they probably like they might not have. It's like the coolest thing ever. I don't know. I think it's like I also really like the dark forest paradox, like the hypothesis. Yeah. That's really cool. So that's a wrap for today, and we hope you guys enjoyed what we talked about today, and we'll continue producing these monthly, and we'll have different topics every time. And yeah, that's about it. Anything else you guys want to say?
Disclaimer. We're just teenagers. Don't take
Yeah, we keep reiterating this, yeah.
Thanks for watching.
Yeah, thanks for watching. Bye!